So let me quickly review what we did. So there was a source and there was a problem of transmitting this source or compressing this source, representing it using binary strings. And there were two objects that came out of this. One was the transmission cost of x, which amounted to assigning prefix-free code words to x1 to xn in such a way that the expected length of the code word is as small as possible, and that was a very practical sort of a question. But in our analysis of that question, a formula popped out, and this formula is entropy, which the word which you have heard in various contexts, and yeah, so it has a slightly awkward form, but it's a very important function. And its importance at least was partly explained by Shannon's theorem, saying that entropy sort of quite closely characterizes the transmission cost. Okay.
So this idea of entropy measuring information came because of this, not from the earlier definition of entropy.
No, so entropy as a notion of information, I don't know how prevalent it was in the physics community, but so it is, see, every formula, I mean, there is somebody's theorem, is not due to the person it is named after. Okay, so the Shannon entropy is actually, it turns out that in the 1910s or something, somebody named Hartley or some, I forget the name. So he had already written this down. Okay, but in today's understanding, or at least the story that I'm trying to convey, this is why I would like to call h of x a measure of information. Okay, because it tells me how much effort it takes to transmit that information. Okay. Now, we did some mathematics, and there was this inequality which had a very nice modern proof by introducing randomness. That is, we imagined the code words on a tree and somehow decided that we will take a random walk down the tree. Yeah? So this is one of the ways of proving things in combinatorics nowadays, which is called the probabilistic method. Okay? So the statement itself doesn't have a probability. There are no probabilities in this statement. But nevertheless, you employ probability or imagine a probability in order to better understand it. Okay? So, but there was a pleasant thing about this inequality, that it almost has a converse if you think about it the right way. That is, if you are given some lengths and they satisfy this, then there exists an encoding with the corresponding lengths, prescribed lengths. Okay. Now, in the course of proving Shannon's theorem, we applied, we used the fact that log is a concave function. Yeah, and so there was this probability P1, P2, Pk. Sorry, here I've made it n, but the probability that came from the source, and there were the numbers 1 over 2 to the L1, 1 over 2 to the L2, 1 over 2 to the L, which also, like, but for the fact that this is an inequality, if this was an equality, we could regard these numbers also as probabilities. Yeah, and there was this summation log pi log some 1 over 2 to the Li, which, and then we used the concavity of log to prove this. Okay, but what we did is a special case of a general inequality which holds, well, yeah, suppose P and Q are two distributions or two probability vectors with the same number of outcomes, then this quantity summation pi log pi over qi is always greater than or equal to 0. Okay. It's kind of a strange thing in the sense that you can think of PIs as a histogram, and QI is also, yeah, so both of these somehow add up to 1. Now, for some I, Pi may be bigger than Qi. For some of them, Qi may be bigger than Pi. Yes? So, if Qi is bigger than Pi, then this number is less than 1. The log of it is negative. Okay? So, in this sum, there are negative and positive terms. But nevertheless, the sum is always greater than or equal to 0. And the reason is the same, that is, you don't prove this, but you try to prove that summation Pi log Qi by Pi is less than or equal to 0. And I've just multiplied it by -1 on both sides. And now to this, yeah, that's right. So previously we used to have 2 to the minus Li here, and now you have Qi's here. So this, I don't know, you would probably, yeah. If you use the concavity of log, the Pi's will cancel and you'll be left with this, but, sorry? Yeah. Okay. So that's all. Okay. And this inequality is called Gibbs inequality, and some of you might remember. So Gibbs, physicist from the 19th century. Okay. So such an inequality was already written in the physics literature. Yeah. Yes.
What are QIs?
QIs are some other things, some other probabilities. We don't know what they are. So I will link it to the thing. Yeah. So good. So right now there are two probabilities, Pi and Qi, and this is a measure of how different they are. If Qis were exactly the same as Pi's, each of these ratios would be 1, their log would be 0, and this number would be 1. Okay? But as Pi's differ from Qi, this number goes up. If Pi is equal to Qi, I mean, that's not because I say so, that's because you see it. Pi equals Qi, then each of these numbers is 1, and then it will be 0. Yeah? But whenever Qi is different from Pi, then this number is greater than or equal to 0. And how different this is has importance in many areas of mathematics and statistics. Okay? And yeah, so this is.
Is that, thinking aloud, is that some sort of conditional formula?
No, this is called relative entropy of P and Q. Okay? And no, I just want, since you asked, what is the relationship with transmission? Suppose somebody built a code. So there was this source, and somebody built a code, and they placed their code words at various places. Yeah. Yeah. Okay, so there are 4 symbols which needed to be encoded, and they gave these code words. Yeah. So this was, let's say, L1, this distance was L2, L3, L4. Yeah, this length was L4. Okay. Now, do you think this is the optimum code? They didn't use this at all. Yeah. Could this be the optimum code for this problem, assuming all probabilities are positive? No. What could you have done?
Just taken L2 to the top, right?
You could have moved it up. Yeah. Okay. So now you move it up. Now, once you moved it up and you think in terms of your random walk, then each walk would definitely pass through one of these 4 things. That means this summation 1 over 2 to the Li would actually be equal to 1. Yeah? Yeah. Which is what okay. So these numbers 1 over 2 to the Li's can also be thought of as probabilities. Yeah. So think of 1 over 2 to the Li's as Qi's. Yeah. So with that, what is this quantity measuring? Summation Pi log Pi And instead of Qi, let me substitute, sorry, 1 over two to the Li. Yes. So what is this measuring? Summation Pi log Pi and minus summation Pi Li. Did I do that right? Sorry?
Shouldn't it be 2 minus, it should be plus, right? 1 by 2 goes to the top. Okay, that's 2 to the power negative Li. 1 by 2 to the power negative. Yeah, it should be plus. It should be plus.
That's good. Yeah. 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 So this is minus h of x plus t of x. Is that right? I don't have a minus because this should have been 1 over pi. Yeah. Or just to be very clear, this is t of x minus h of x. Yeah. Now, h of x is the best you could do. That's a law of nature, says that you can never do better than h of x. And t of x, this is not exactly t of x for this particular encoding. Yeah. And the difference you can think of as the regret. This is the best you could have done according to Shannon's formula. This is what you are achieving. And the difference is the regret. That is, how much are you paying more than what is the absolute information theoretic optimum. Okay. So relative entropy, you can think of it as the non-optimality in this context of the code. Non-optimality with respect to not the best engineering solution, non-optimality with respect to the ideal thing where you were allowed even real numbers for the LIs. That difference is there. Now we know that this is always greater than or equal to 0 because of some theorem. Yeah. Shannon's theorem. Yeah. That is, Tx minus Hx is always greater than 0, but how much greater is governed by this, where for Qi's you write 1 over 2 to the Li. You had a question?
Is the D of P comma Q, is that a distance metric?
No, it's not a distance, it's not even symmetric.
The next question I have is that I don't entirely see how we are getting summed to one thing. The only assumption we have that it's summed to less than 1, right?
That's right. So it is only less than 1, but I'm saying I kind of played a little game. If it was strictly less than 1, you could have done something locally to get something better. So once no local improvements are possible, then it will actually be equal to, because you could always have shifted the code words up. Okay. Yeah. For us, let's assume that all the PIs are positive. Yeah.
I think you were alluding a little bit what, in a communication context, what is QI?
So QI is, so we said if you are given PIs, you try to construct your code so that your length of the code is log 1 over PI. Imagine that somebody did not know PI and they had assumed that actual distribution was QI and they went ahead and built the code according to QI. Okay. What is the cost that they need to pay for having built their code assuming that the distribution was QI when the actual distribution was PI? Okay. Because the length of the code word that they would use is log 1 over QI. Yeah, when they should actually have used log 1 over PI, because they did not have a good estimate of the probability. What is the difference between the optimum and this suboptimum, which you, the suboptimality because of this, yeah, ignoring all those plus ones, etc.
That's why it's non-symmetric.
It's non-symmetric, you know one thing, you don't know. So various stories can be made. This is not the best story for relative entropy, but having come this far, I just wanted to tell you that there is an interpretation of relative entropy as the regret for not having known the distribution accurately. Okay, don't take anything I say very seriously. Okay, yeah. Okay, good. Yeah. Even this one. Yeah. Okay, good. So we were here, Yeah, so this was an inequality which sort of we encountered indirectly, but I wanted to make it explicit. It has a famous name associated with it. Good. Sorry, this is also called, this quantity is called the Kullback-Leibler divergence. Sometimes it is, they take PQ plus QP and then call that to make it symmetric and things like that, but yeah. And sometimes they change the logarithm to the base E, various things happen, but roughly that's the spirit, okay, good. Now, the point I was trying to make towards the end of the last session was that suppose you have an instance of that which corresponded to a coin toss, yeah. So here was a coin which showed up 0 with probability 0.25 and 1 with probability 0.75, and another one which was 1/3 and 2/3. Now, for some reason, we go ahead and compute the entropy for this fellow and compute the entropy for this fellow, and I did the calculation, and this one comes out to be 0.811, this is 0.919, okay. In general, the binary entropy, so ZP means it takes the value 1 with probability P and 0 with probability 1 minus P, the Bernoulli coin toss with probability P. So the entropy is maximum at half, at 1 and 0 it is 0. When, if it's a completely determined coin toss, P0 corresponds to it taking the value 0 with probability Z0 corresponds, yeah. Whereas when P is 1, it means it always comes up head, yeah, yeah. So, but there is 2/3 and there is 3/4 and there are these numbers 0.811, 0.99, etc. Now, do they even have any meaning? Because the so-called transmission in both cases, the transmission cost is 1. Yeah? Whether you want to transmit this random variable or this random variable, you will assign one of them something, the other something else. Okay? So it turns out that this thing has a meaning, and that is what I want to explain. Question? For this? Yeah, yeah. So yeah, I have a random variable, and what is, so here is the value of Z. Z can take the value 0 or 1, and it has some probabilities, yeah. So to this I want to assign a code word, and to this I want to assign a code word. So here is your tree. At one of the nodes of the tree, you want to put a 0, and at another node, you want to put a 1. Yeah? Can you put anything here? Because the moment you put one thing, there will be no space for the other. So each of them necessarily have to be put strictly below the root. That means the cost has to be at least 1. Yeah, you cannot do cost less than 1. And if you call this 0 and call this 1, that is this one 0, this one head and this one tail, then you are achieving 1. So that's why T of x is equal to each of these random variables. Okay? Yeah. So each of these random variables has transmission cost 1, but it has different entropies. Okay? Is there a physical meaning to these numbers? Okay? And it does. Okay? And that's what I want to tell you. Okay, so this is Shannon's theorem for instantaneous coding. I'll now tell you why it's called instantaneous coding, or what else could we have done. So just hold on to this. I will tell you something now. So So you have a random variable. We'll get back to the z. We have a random variable x, and suppose we sampled from it again and again. Okay. So x1, yeah, I have changed the role of, maybe I'll use t. Yeah. So I sampled from this t times. Okay. So what is this composite object now lives in a space of what size? T-dimensional space, yeah? And how many points are there in this T-dimensional space? There are n possibilities for each of them. So this lives in x1 to xn to the power t, so whose cardinality is n to the power t. Yeah. Now there are various strings here, and each of them, these are strings of x1 to xt, x1 to xn. Yeah, these are strings of x1 to xn, and each of them, let me call it x bar. Yeah, so each of them has its corresponding probability. So suppose this string was x1, x2, x1, x1, x1 again. So it was x1, x2 once, and all the other times it was x1. Then what would its probability be? Independent.
T1 to the power t minus 1
into P2. Okay. But if this x2 was, there is a symmetric object here where it was x1 all the time except for x2, it would be the same probability. Yeah. So there are many strings here which have the same probability. Some other strings have various probabilities, etc. Now, instead of being too eager to encode each xi, yeah, the engineer says, you know, I will wait for t turns, see the pattern I get, and try to assign that a code word. Okay, yeah. Now, why should it help? The engineer makes one more assumption. That is actually, you know, it is okay if I don't encode all the strings. A probability delta of them I'm allowed to ignore. Yeah, that is, I want a system where if my string is not typical, it's not a string which is expected to have good probability, then I'm willing to ignore it. Okay. Now, of course, each string has minuscule probability because we are taking products of these numbers. So what I say is that I want a large set of strings so that I will devote my attention only to those strings and encode them. But this large set is not in terms of numbers. This should be a large set so that it covers a substantial amount of, substantial. Yeah.
So just to get the notion is that you should see that space with probability 1 minus 10.
That you should see that probability in the product space.
Yeah.
In the product distribution, you should see it with high probability. Okay. Yeah. So yeah, go ahead. Yeah.
When you ignore stuff which happens rarely,
Yes.
are you saying that, like, I don't care if they get decoded at the other end?
It could be that whenever such a symbol happens, such an outcome happens, so it may be that you have a lab here and your collaborator is in Germany, they asked you to perform an experiment and transmit the outcomes. You just tell the fellow, actually, you know, it's a very awkward outcome, we haven't yet fixed up the code for that. Okay, let's do the experiment again.
Because in some, like, an alternative way of looking at it is that rare events are more precious.
Depends on your attitude. Yeah, well, no, you're right. Yeah.
You're trying to fix a explanation to that phenomenon somehow.
Yeah, so, but it,
Outcomes, they just have one expectation.
yeah. So let me write down something.
I mean, there's no kind of sign, there's no engineering you can just,
Well, since delta goes to 0, yeah, and very soon we will be talking about channels which make errors, okay. So if you keep your delta so small that the chances of the transmission error are already greater than the error with which you are neglecting certain outcomes, then you can live with it from a practical point of view, okay. Yeah. But I'm writing a definition here. Yeah, please just see. Don't worry too much about this. Sorry, my font changed. Okay. So what am I doing? This set is my A. Yes?
X to the T or X to the N?
No. Since I've written N here, it is the T of this, but no, since I have a different N, I'm really sorry. Yeah, my notes were from a different time. Is it okay? Yeah, there's, yeah, okay. So what did I do? I first tried to find a set here which has a large amount of probability, yeah, and to each of them I assigned a code word, a different code word. Yeah. So suppose I picked up L strings here and I assigned them all code words of the same length but different code words. What would L be? Log of the number of elements in the set, because each of them has to be sent this, okay. So what is my engineering task now? Under the allowance of delta, what is the set of smallest cardinality that I can choose so that I'm able to encode all of them accurately, yeah?
Why do we care about 1 by T?
So since this is per experiment the cost. Okay, so suppose I didn't have this one. Yeah, this is the cost of transmitting the outcome of T experiments. Yeah, number of bits I need to transmit the outcome of T experiments. So to compare it with h of x, which was after all designed to transmit 1, let us use the same currency. So we divide by T.
So what do you mean by log of mod A?
Log of mod A. So this A is a set of strings. Mod A is the number of cardinality.
So we're saying that just take the log of the number of elements of cardinality.
No, yeah, so that's right. So look at this number and suppose that number you got was 2 to the power 50. Okay, so the first one, arbitrarily, you assign it a code 00050 times. The next one, 00001, and so on. And you have 2 to the power 50. So each of them will be assigned a different fixed length code word of length 50. So now their actual probabilities don't matter. The amount, in any case, that you are sending for every string in this place would be this, and you are trying to minimize. Is this okay? Yeah.
For all points in A, the length of the code word is
Is the same. This, I should probably put this, but don't worry about this. I'm dividing by T. That plus 1 is going to be washed away by T. Okay, is this okay? Yeah. I mean, yeah, I've taken a sort of a leap in notation from the baby things I was doing. So please ask me if something is not clear. Now the theorem. This is Shannon's, you can say, source coding theorem. is that limit for all delta greater than 0, limit as n tends, t tends to infinity, so previously there was this +1 fuzzy business, but once you adopt this point of view, yeah, I will try to explain why this is meaningful. Then actually this is entropy captures the rate at which the set grows. Now, when you have, so the set grows when you take products. Yeah. So suppose you have, like back to combinatorics, suppose you had a set 1, 2, 3, 4, 5. Yeah. Okay. Now what is its cardinality? 5. Okay, good. But let's call this set S. S squared. What is the cardinality of S squared? Yeah. If I took S to the power t, 5 to the power t. Yeah. And you can imagine that if I took the log of this and divided by t, you would get some number which is something like 5 or log of 5. Okay. So you can, instead of saying what our high school teacher taught us about cardinality, we say cardinality is not the number of elements here. Cardinality is the base of the exponential that comes up when you take products. When you take the original set and take its products, the size of the set grows at a certain rate. And the rate at which it grows is some constant to the power t, presumably constant greater than 1. Yeah, the set doesn't shrink. Yeah. And that constant is called the cardinality. Okay. Now, having adjusted ourselves to this notion of thinking about cardinality, I have a probability distribution. Not all elements are the same. This was where all elements, we are not differentiating between 4 and 2 and 3. They are all the same for us. But suppose they were weighted. They had probabilities associated with them. Then we say, look, we don't want to encode the whole thing. We don't want to encode. We just want to encode. We could even say that maybe some of the PIs were zeros. Yeah? Then those strings here would have 0 probability. Any string which has, suppose P1 was 0, any string that has x1 in it anywhere would have 0 probability. Yeah? So we don't want full measure either. But we want a good fraction. Wholly. Wholly means every single string has to be encoded. But then the number is n to the power t. And yeah, then you can't do anything better than log n. If you took n to the power t here, took the log of it, and divided by t, you would have been left with log n. Okay? So if you did wholly, you would get log n. If you did full measure, suppose out of these n strings, only m of them had probability. The others didn't have. Then full measure would then give you log m. Yeah? But we are saying no, neither wholly nor with full measure, but yes, substantially, meaning at least 1 minus delta. Yeah?
So delta is not showing up in this theorem.
For every delta greater than 0, maybe less than 1. Yeah? So if you try to get 10% of the mass, you will need entropy. If you need 90% of the mass, you will still need entropy. Okay? The rest, the lower order terms, are being killed by dividing by t. Okay. Is that okay? So, question?
If one of these probabilities is 0,
Yes.
so when you look at a string
Yes.
and let's say x2 was 0, for example,
Yeah.
then x1 will have a non-zero probability, but x2 has 0.
Yeah.
Like how
How can that ever happen? Yeah, no, I mean, so if you toss the coin first, press the button here, x2 came up, then you press the button again here, x7 came up, and you did it t times. So you got some pattern. Patterns which have x1 anywhere in them will never appear. So when the sender and receiver are negotiating about the code word, they will say, let us throw away those strings which have an x1 in them. Anywhere, because they are not going to happen. Okay, so why invest in them? Because investing them amounts to encoding the whole space. Okay, sorry. Yeah, so we don't encode the full space anyway. We don't want to even encode everything which has some probability. Okay, but we want to collect enough strings so that we get at least 10% of the probability, actually ideally 99% of the probability. And then we ask how much do we need to invest in transmission cost, and it turns out that whether it is 90% or 10%, that delta is not relevant. Okay, the number is always the same as t goes to infinity, and it comes out to be h of x. Okay, question? Where we do encoding. Yeah, so to each of these strings we enumerate them. This is your set A, all the strings of A you write them, and to each of them you assign a code word of length simplest method, all of them same length. Okay. Yeah? Let me question. Yes. Well, if you're estimating, I assume that you're getting samples from this source, but if that sample also comes with its probability, because it's just come, you got a string. We don't know what its probabilities are. Yeah. We are just getting these samples, but from that, how do you propose to compute the entropy? No, but the encoding is not being given to you. You have got these abstract symbols. Then even one string is enough, because the length of the string would, at least this is a fixed length encoding. Yeah. Yeah.
So how is your typical set measured with the total of transmission?
That's right, I'll tell you. Sorry, so is this roughly clear? Let me just, so there is a corresponding for, I'll come back to you. Yeah. Suppose you had continuous distribution, something like this. Okay, maybe this is 0. Yeah. Now this is your x. It's a real number. Yeah. And now consider x to the power n, independent. So what happens? You are in some high dimensional space, and you have probabilities smeared over this. Some things have higher probability, some things have slightly less probability, and so on. Okay. Now, you want to ask, what is the volume of this distribution in the sense of cardinality? Yeah, sets have cardinality, objects in RD have volume. Okay. Now, what do you mean volume of this problem? This assigns probability to the whole space. Okay. But suppose I say capture in this enough volume so that you get 1 minus delta.
So locate a subset of volume 1 minus delta
under this measure.
Okay.
Yeah, look at its volume. It's n dimensional volume. Take its log and divide it by t. Okay, and define that the real content of the distribution. Okay,
a measure thing, but then we measure the volume with the Lebesgue sort of the set.
I mean, yeah, so let's assume that you pick a measurable sort of set. Yeah.
Yeah, everything measurable.
Yeah.
So we locate 1 minus delta measure
Set.
measure according to this guy first.
Yes.
But then we take its volume, actual volume.
Actual volume with respect to the standard distribution R.
And then we maybe normalize it by the dimension.
By the dimension, because of course it's going to grow exponentially, and that quantity is also an entropy which can be defined for continuous distributions. Yeah, that's called the differential entropy. Okay, so now you see, as you take products, the volume of course grows, but we should not just say that the volume is like infinity. If the distribution is concentrated here in some part, these strings, of course, we can't ignore them. But if they keep appearing again and again, far away in the tail, they should be ignored. Yeah? So if you cut them out and focus on only things that matter, 99% of the things, then their volume grows with n at a rate, and that rate will be the differential entropy of the underlying distribution. Okay? But you had a question. Yeah.
Sorry, I was just going to ask that we have gone from this volume thing is when we have continuous entropy, right?
Yeah.
But right now we're only talking about discrete difference.
So what, yeah, so discrete what we call cardinality, in continuous we call volume.
Okay, that's all.
That's, I mean, I'm just trying to make all kinds of fuzzy connections, okay? Yeah, so but the point is that entropy captures the content of the distribution in this sense. That is, if you take IID samples, how much space does this probability actually occupy? Of course, the probability occupies the whole space. Yeah, but in the sense that if you fix the number delta and take t to infinity, you will need larger and larger volumes, but the volume is not growing arbitrarily. There is a base to the exponent, and that base to the exponent is the differential entropy in the case of continuous distribution. The base to the exponent is Shannon entropy in the case of discrete distributions. Question?
So I suppose, I mean, here we have two different measures. One is our distribution x, the other is
Counting measure, counting
If
measure.
you replace the counting with another measure, do you get the Kullback-Leibler thing or some?
No, you get differential entropy. Oh, yeah, if you, maybe the relative entropy with respect to, yeah, you'll get that.
So what do we get for Gaussian? Do we know, like, for Gaussian? What
Yeah, so Gaussian we have. So it turns out that of all the distributions with a given variance, yeah, the one that has the maximum entropy is the Gaussian distribution.
But it has a number, like it's not infinite or anything.
No, no. It will have a log, it will have a square root 2 pi.
All the E and everything.
Yeah. So actually in my notes it's an exercise. Compute the differential entropy of the Gaussian distribution. So, yeah.
The more concentrated the distribution is,
Yes, they
lower the entropy.
lower the entropy. Yeah.
In our context, that should be XT.
Yeah, in our context this should be xt. Yeah. Yeah, sorry. Yeah. Question.
When we're talking about the differentiable entropy of the Gaussian, you mean the Gaussian is over the x1s to xn?
No, the Gaussian is over the reals, and then you define differential entropy of any distribution as you write a smaller x, because, and then you write minus integral r, yeah, and if the density is so for Gaussian f of x will be, this should actually be little x, huh? And you are integrating over the reals, yeah, and f of x is 1 over square root 2 pi sigma little x. Yeah. So you instead of doing this discrete sum, you do this, and that captures this notion. Okay. Good. Is that okay? Yeah. All right. So this is all I wanted to say about entropy. Of course, there is much more to say, and some of you might have noticed that I tried to pun here because yeah. Shannon's theorem came in whatever, ni- ni- 1949 or something, but not far from here, a speech was made in 1947, which said wholly and full measure and substantially. Yeah. Yeah. Not wholly or in full measure, but substantially. Yeah. Yeah.
Are we now finally going to relax the
Yeah. No, you can relax now, and yeah. Good.
All of this seems to be related to law of large numbers.
Yes, it's
Even the fact that Gaussian distribution turns out to be the maximum, can that be connected to central limit theorem in some way? Or?
yeah, that I don't know. Yeah, but there is a version of KL for this, and yeah. So,
How do we prove this?
sorry,
How do we prove this?
prove this one. Yeah, yeah. Okay. So let me just give you an idea. Somebody said typical sequences. If you take T large, how many of these strings do you think, how many times will x1 appear in this experiment of length T? About P1 times T, P2 times T, and some, yeah, Pn times T. Yeah. This is the number of times x1 will appear, number of times x2 will appear, number of times xn will appear. Okay. So how many strings, because the remaining strings where this number deviates from P1 or P2, they will have very small probability. Okay. N is fixed. You can even do a union bound over n and say that strings where these symbols don't appear their expected number of times, much different from that, would have very low probability. How many strings are there which have these many x1s, these many x2s, these many xn? Multinomial coefficient T times P1T, PNT, yeah, this multinomial coefficient. So basically, if you take the log of this, that should be the answer. Okay. Now you do your Stirling or whatever, and when you do this, well, yeah, or in other words, each of these strings has what probability? It has any string which has this composition has probability P1 to the power P1T, P2 to the power P2T, Pn to the power Pnt. Yes, because you have fixed the positions where P1 appears, fixed the positions where P2 appears, etc. This would be its probability. Yeah. How many such strings do you think we need to connect in order to get 1 minus delta probability? Well, if all your strings have this probability, then you do 1 minus delta divided by this number. Yeah, if you believe everything. And if you take a log of this, forget the log 1 minus delta and plus, yeah, I mean, yeah, so if you're going to put a 1 by t here, you would put a 1 by t here, and yeah, 2 to the power, yeah.
So the main thing you really used was
So
saying that strings that don't behave like this won't show up, and that's just.
yeah, strings, so it is not only that this is a substantial part of the probability, all those strings roughly have the same probability, which is about this, yeah. So, is that okay? Yeah.
But this is just because of law of large numbers.
The fact that probabilities don't go away, like strings other than these or close to these, yeah, is because of law of large numbers. Oh yeah, and yeah.
That says T times centrifugal, not 2 to the power.
Sorry. Oh, I've already taken a log. Okay, yeah. So
all the points in 1 minus delta are have
so let me do it again. Sorry. So my channel might get a little postponed, but let us fix this for now. Okay. Let us get back to our Zs. Z 2/3, let's say. What was this distribution? It took 0, 1, 0 with probability 1/3, and this with probability 2/3. Okay. So if how many strings are there in the space if I take the product t times? 2 to the power t. So my space here, to be concrete now, is 2 to the power t. Okay. Now there are strings. Let me draw it slightly differently. Yeah, yeah. Which string has the most probability? All ones. Yeah. And why? And what is its probability? 2 by 3 to the power t. Yeah. And which string has the lowest probability? All zeros. And these are strings which have 50% 0 and 50% 1. Their probability looks like 1/3 to the power t over 2 and 2/3 to the power t over 2. How many strings are here? Yeah. But if you perform this experiment, the strings that they appear will have how many ones most of the time? This layer, yeah, plus or minus width of square root n, yeah, square root t, yeah. So there is this narrow band here which has this. If you want to capture 1 minus delta fraction of the probability, you better attack these. These may be very tempting. They have very high probability, but there are only few of them. Okay, they are irrelevant. The relevant ones are these. And how many of them are there? Do a calculation like this. Sorry, I removed my multinomial coefficient. So here it will be a binomial coefficient. T, 2/3 t, 1/3 t, if written in the multinomial way. And how many of them are there? Basically 2 to the power t times h of x. If you change from z 1/3, 2/3 to 0.25, 0.75, this layer will be located if it's a completely fair coin, it will come in the middle. And how many strings are there in the middle? T choose t by 2. And all of us, we are taught that this number looks like some pi's, etc. But then when you take the log of this and do 1 over t, all this square root 2, etc. doesn't matter, and you are given 1, which corresponds to the entropy of a fair coin toss, because you are in the middle. If you are an unfair coin, biased coin toss, then you are here. If you are more biased, higher. If you are really like determined, then all your probability is here. If you want 1 minus delta, you have to better pick that one. But then there is only 1. Log of 1 is 0. Okay, so somehow there seems to be consistency with our intuition. Yeah, and the theorem says this is what is going on. Okay, whether you want to pick 0.9 or 0.1, it makes no difference. All right. Okay. So, I mean, is it okay? Can we just spend 5 minutes on? Yeah. Sorry, I've been like beating about the bush and saying various things around entropy. I hope all of them, at least a significant part of them, was useful. Yeah. Substantially useful. Channel. Channel. Yeah. So what's a channel? So channel has 2 alphabets, okay, X and Y, okay, yeah. So X has some N symbols, and Y has some M symbols. And a channel is something to which you can feed one of these input symbols, but the channel is not completely faithful. When you feed it x5, it sprays its probability over various things. Yeah? If you feed x1, it probably favors these strings, but it can go here. Okay. So such an object is called a channel. It is a matrix. When you feed x1, the various yi's come up with this probability. When you feed it xn, so it is a well-defined stochastic matrix. Yeah, stochastic in the sense that each column is a probability vector, and these numbers are given to you. And when these numbers you might call are the channel's characteristics. Yeah. Now, an example. Let us consider coin tosses or binary alphabets for both input and output. Yeah. So the input alphabet is 0, 1. So here is a channel to which if you feed a 0, the other person at the other end is most of the time likely to see 0, but with probability epsilon, they will see 1. And similarly, when you feed a 1, it gets flipped. Whatever you send gets flipped with probability epsilon. Okay. Now, how would you do a transmission? Yeah? So you have some large number of messages to send, M1, M2, Mn. I'm writing capital N. Yeah? So these are the n messages that you want to send. Each of them you would like to encode it.
To be as general as possible, the epsilon when you transmit 0 and when you transmit 1 could be different.
Could be different. I mean, this is general. This is a particular case. Maybe I should give you one more example, but that also may not appear too general to you. But 0, 1. So if you transmit 0, it comes out as 0. With probability epsilon, it gets erased. Okay, but you see that it has been erased. It's a smudge. Okay, you send a 1. If it is not smudged, it's seen as 1. Otherwise, you see that it has been smudged. It's not so evil that it substitutes a 0 for a 1. It tells you that I have made an error, but I'm not telling you what was transmitted. Okay, so this is called binary erasure channel. And this is called the binary symmetric channel. Yeah. Now,
strings of 0, 1s?
there are some abstract messages. You know, in olden days, we used to go to the post office and say, please send 0, 1. Yeah. Mother and child doing well is received on the other end. Yeah. 0, 2, best returns for the day. Okay. Those are the various messages here. Each of them, to them, we would assign a code word, let's say of a fixed length. You would feed it through the channel. Sorry, I will stop soon. Yeah. Encoder and decoder. the telegraph office receives one of these messages to be transmitted to the other side. It converts this message into a sequence of zeros and ones, okay, and feeds it to this channel. The other channel now receives another sequence of symbols, and when it compares it with what the telegraph office was supposed to send, it doesn't match at all with any of them. Why does it not match? Because some zeros have been converted to ones and some ones have been converted to zeros. But is there a strategy so that the decoder says, look, you know, if it was a birth, I'm not going to decode it as a death. Yeah? Most likely, on receiving this, it must have been this message that was intended. It gives it to the receiver. Okay? So we would like an encoding process and a decoding process where, so ideally if there was no error in this channel at all, then we could have gotten away with log n bits. Each of them we will give a different string, yeah, of log n bits. But because there is error, we will have to add redundancy to our encoding. That is, you will need t bits instead of, let us call this to be 2 to the power n. Yeah. So where you could have gotten away with n bits without error, now you are having to send t bits with some specified error parameter, and this t over n is your rate of the cost per symbol. Yeah, cost per bit of information, because the input had n bits of information, and you are having to transmit t bits of information just to send n bits.
Just to account for the fact that it is lossy.
It is lossy, and this quantity, now just as we did the engineering problem, we can ask, I've given you this channel characteristics, design the best encoding and decoding scheme so that this quantity is minimum.
No, but then how do you talk about redundancy in that regard?
I don't say redundancy. My definition of redundancy is how much did I need to transmit in order to send this minimum.
No, okay, so my question is, how do you encode the constraint? Because ideally, then I'll just say send those n bits as it is, right?
You send that n bit, then the channel makes an error, and then the decoding, we would require that the constraint would be that
Decoding is correct with high probability.
probability for x belonging to so this will be a constraint that design a decoder and an encoder for a t, yeah, for n, so that this quantity, and then as n becomes bigger and bigger, you ask how much do you need, and you compute this quantity, and you call this the capacity of the channel or something. Yeah, the best encoding is the capacity of the channel.
So we don't have any probability distribution over the x itself.
You can either say, yeah, we don't, for every x, no matter, yeah, what message you want to send, it must with high probability be decoded correctly.
That matrix which characterizes the channel.
Yes?
I was just thinking there's also a temporal dimension to it, right? Like at
It's a time dependent, yeah. So right now we are thinking of encoding where the channel is stationary. That is, at every time, whether it is the 5th symbol or the 7th symbol, its characteristic stays the same. Okay? But it could be that as you are transmitting, your antennas are getting heated up, and then zeros are being, yeah, or there could also be, depending on the time of the day, changes. We are living with simple examples where everything is IID. Yeah.
Or we can assume that at every time instant we have that matrix.
We have that matrix. Yeah, we could do that. That's, yeah.
You're saying matrix is a function of time.
Matrix as a function of time. Yeah, but the simplest Shannon theorem that I'll be able to tell you is for matrices which remain the same, and whether you use it the 5th time or the 7th time, the characteristics are the same.
So if once we fix the delta, asymptotics don't change, means the delta here also.
Delta, for every delta it is the same. In other words, we will, for every channel, for every channel, there will be a capacity. We will associate a number called capacity, which will have mutual information in it. Mutual information of which random variables we'll have to discuss. Okay, I was hoping to do it now, but it's okay, next time. Yeah. If you try to transmit below the capacity, then your fidelity, your success probability will be close to 1. Yeah. But the moment you try to transmit at a rate which is higher than capacity, you try to stuff in more messages than the capacity allows, then your probability of success will go to 0. This is very sharply, like, yeah, as n goes to infinity, it basically does it here. Yeah, but no, this is not the Nyquist rate. This is the Shannon capacity of the channel.
Okay, so this is the theorem.
This is a theorem, but we have not written it. We'll state it that there is, with every such matrix, just like with every probability vector, there was a number which was h of x. With every probability vector, there was a number that was called h of x. And that h of x, by now, you know what it means. It means the transmission cost, it means the volume growth, it means many various things. Okay? In the same way with every stochastic matrix, when viewed as the characteristics of a channel, there is a number associated, and that is called the capacity. And that capacity represents the rate at which you can push information through the channel. Yeah? For example, if this epsilon was half, that means whether you transmit 0 or 1, the other side is seeing a random bit. Yeah? The formula will tell you that the capacity is 0. Such a channel cannot be used for any transmission. Okay? On the other hand, if epsilon was 0, then whatever you send is received faithfully, then the capacity would be 1. Yeah? Because to send one symbol, you will not have to add any redundancy. You can send it as it is. Okay? But in between, what is the best number? Okay, it looks like a complicated engineering problem, and especially when I'm saying asymptotically as t goes to infinity, n goes to infinity. But in the end, it turns out to be a formula. Okay? So the conditional distribution of what is being received, yeah. Right now I have no distribution in this at all. So I will have to cook up a distribution on the input symbols, and that would give rise to, when it is pushed forward, it will give rise to a distribution here, and that distribution will, so these will be correlated random variables, and they will have a mutual information. I'm sorry, I'm going to repeat everything tomorrow, okay? So yeah, please hold on. Yeah.
How is the coding theory, all of this?
So the question is, Shannon's theorem tells you that in principle, you can transmit at this rate, okay? But when you are given a particular symbol, how should you encode it? That is the art of coding theory. That is explicitly constructing code words.
Separately from information theory?
Yeah, these kind of, they dance around, I don't know. I mean, there's this, I don't know, in Maharashtra we call it thugdi, like, you know, yeah, so yeah.
And practically as channels have gotten better,
Yeah.
You need less fancy coding skills.
No, our ambitions also get better. Yeah, yeah. So there are various things that happen. Yeah, yeah. See, it's not so simple. When you send something through an antenna, yeah, there is not only one antenna. It's not point to point. Okay, array of antennas, and then each of them has a characteristic. And then you are not the only one who is transmitting. There is everybody who is transmitting. And then you interfere not with only with your messages, but things. And sometimes an antenna picks up not what you sent, but what you sent and got reflected off a wall. It's like life is annoying. Yeah. But math is okay. Yeah. So can I stop here? Thank you very much for